All right, so welcome to the analytical dynamics class. As I said, as has been written down as planned before, the very first topic is about review of Newtonian mechanics. Yeah, so I'm gonna start this course with review of Newtonian mechanics. Now, I'm sure that all of you are very familiar with Newtonian mechanics. Oh, by the way, if you want to ask a question or you feel that there is problem with the connection, that my voice couldn't be heard, or that the screen freezes, please raise your voice, because I cannot see your camera, so I cannot know whether you have any problem or not until you raise your voice.
Yes, sir.
All right. So I'm going to start with a review of Newtonian mechanics, and I'm sure you're familiar with this topic, yeah, since you're undergraduate or even your high school. But I want to just underline several fundamental concepts that maybe you have discussed in the undergraduate, but you overlooked it. And for the first part of the review of Newtonian mechanics, I'm going to start with mechanics of single particle. Okay, maybe I think it's better if I make a plane, because all right. So, and by the way, please forgive my bad handwritings, yeah, because writing in the board like this is not very easy. So, well, my handwriting itself is not very beautiful, and moreover, it gets worsened by the fact that writing like this is not very easy. Yeah. And that's why I picked this type of platform, the journal, because for other platforms, sometimes it's harder for me to write in a good way. So yeah. All right. Anyway, so let's jump into the topic. You know, the fundamental problem of mechanics, I mean, all problems in mechanics is always that we are given a state of a particle. What I mean by state is that we know the mass of the particle, we know the velocity of the particle, and by the velocity we know the momentum of the particle, right? And also we know we are given information about all the forces that work on that particle. Okay, let's focus ourselves now on a single particle. So there's only one particle. Yeah, I have one particle, and the particle can be modeled as a point particle. Okay, so it's a point particle. It has no shape. It has no geometrical structure. It has no a distribution of mass. It has only mass. Its total mass. Yeah. And then we are given information about its velocity. Let's say it goes to some direction, the velocity, okay? Or maybe instead of the velocity, I'm just going to, let's say that I'm going to put this particle in a two-dimensional or three-dimensional coordinates, yeah. So this is, let's say this is X, this is Y, and this is Z. So this particle lives in a three-dimensional coordinate, okay? And so we can, let me just put the mass here. Yeah, has mass, and well, we can always define what we call the position vector, right? I call it R. Yeah. So R is the vector that describes the three-dimensional position of the system, right? So R here, it consists of X of I plus Y of J plus Z of K, right? I, J, K are the basis vectors of X, Y, and Z respectively. So basically the R tells us where is the particle in X direction, in Y direction, and in Z direction, okay? Well, from Newtonian mechanics, we know that once we know R, we can always calculate the velocity of the particle, right? The velocity is just the first derivative of R with respect to time. And by that, in the Cartesian coordinate, by the way, this is the Cartesian coordinate, yeah? So this is just the X dot I plus Y dot J plus Z dot K. Okay, recall that I'm using dot here as derivative with respect to time. So whenever you see something dot means that I derive that something with respect to time, okay? And I'm going to use prime as a symbol denoting derivative with respect to position, okay? So if I said like V prime, that means we take the derivative of V with respect to position. The position can either be X, Y, Z or R, theta, and phi, okay? And from that, we can define the momentum, yeah? The momentum is just the product of the mass and the velocity. So this is what we call the linear momentum, basically, yeah? Linear momentum. All right, I think you are all familiar with all of this.
Yes, sir.
All right. Now, every problem in mechanics starts with the information that what are the forces work on this particle. So this particle may have a force work upon it, or may have more than one forces work upon it, okay? So whatever forces that work upon it, we can always sum them up as one, let's call it F. Yeah, this is all the forces working on the particle. Working on the particle. Okay. And so Newton's second law states that the rate change of momentum over time is just given, sorry, that all the forces, the resultant of forces working on the particle is just equal to the rate change of momentum over time. What I mean by that is that the change of momentum over time is equal to all the forces involved, okay? This is basically the original expression in for the Newton second law. Since in most of the cases the mass is constant, well, I'm saying most of the time, not all the time, yeah, there are cases where the mass changes, it's not constant. For example, in the mechanism of the launch of rocket, yeah, when you launch a rocket, the total mass of the rocket decreases because some part of the mass is burned as fuel, yeah, and it's burnt and it's blown out, okay? So the mass of the rocket in the space is less than the mass of the rocket, the initial mass of the rocket. So in that process, there is a decrease in mass. Yeah, there is a change in the mass. Okay, but this type of situation, it doesn't really happen often. Yeah, in most cases of mechanics, I said most, yeah, mass is basically constant. So for constant mass, we can always write down the equation as this one. Yeah, so it's mass right?
Yes, sir.
All right, so now from the point of view of mathematics, this equation is second order ordinary differential equation. Okay, well, it depends on the left hand side. If we, for some cases, the left hand side will give you partial differential equation. But in general, this type of equation is second order differential equation, and the solution of this differential equation is what we call the uh, the equation of motion. Well, this is what we call the equation of motion. The solution of the equation of motion is basically the R, the position vector. Yeah. Why is it knowing position vector so important? Because once we know position vector of a system or a particle, in principle, we can know the information about that particle for any arbitrary time to the future. Of course, this is classical. Yeah. Classically, once we know the position vector of a particle, then you know the behavior of the particle indefinitely. Yeah. So let's say that the particle behave, or it moves from one point to another. Yeah. Because the position vector records the information that you need, right? And the position vector is a function of time. So for any given time, you can know where the particle is, what the velocity of the particle is, its energy, its momentum, etc. Okay, so in principle, knowing solving this equation, you know about the system or the particle. Okay, and so the problem in mechanics is always solving this equation, right? All the problems in mechanics is always solving this equation. All right, so that's so much for the Newton's second law. Now, sorry, any question? Yeah.
Yes, sir. Sir,
Yeah, please.
Sir, we have considered that this is a single particle.
Yes, it's a single particle.
Yes, so can we say that this is an imaginary particle?
Why is it?
Because it has no proper structure, no proper shape. We cannot say like this. So if we are considering it an atomic particle or a big particle, sir?
Well, we call it toy model. So this is, we model particle like this. Obviously, in nature, there is no real particle that has no structure like this, obviously, right? Or if you want to emphasize, okay, well, we have atom or we have electron. Electron has no structure, fine. But then electron doesn't
Just does not behave.
obey classical mechanics. Electron obeys quantum mechanics. My point is that yes, this is a model, but to a good approximation, in most cases, this model effectively describes real system. For example, if you want to describe the motion of the Earth revolving around the sun, yeah, we can model the Earth as a point particle. Obviously, the Earth is not a point particle, right? But if we look quite far away, if you look far enough from the Earth, we can see the Earth and even the Sun can be modeled as point particles, and the solutions that we get doesn't differ much from the solutions that we would get should we model them not as point particles. Okay, you get what I'm saying?
Okay, sir, got it.
So yeah, this is just an idealized particle. I'm not. I will say idealized model, not an imaginary
Okay.
particle. Yeah. Okay. Now I'm going to talk about the conservation theorem here. I'm going to talk about the conservation theorem, and I'm going to go back to this type of equation many times. So don't worry. We know in mechanics there theorems. Yeah. In mechanics, in general, there are three type of conservation laws. Yeah. The first one is the conservation of linear momentum. Yeah. The conservation of linear momentum. Well, this is very familiar. Yeah. It says that if the total force is zero, yeah, or maybe we can say this conservation law just from the statement here, yeah. So this law, the conservation law of linear momentum, is just a consequence of Newton's law. How can we see that? Well, take a look at this. If the left-hand side is zero, let's say that there are no forces working on a particle, or maybe there are forces, but they compensate each other, they cancel each other. So the resultant of forces are zero. Yeah, those are two equivalent statements. Yeah. Either one, if the sum of f is zero, then the right hand side is zero, right? So if this is zero, then what happens? The right hand side is zero, right? I can put m back to the derivative because m is constant. Yeah, for most cases m is a constant, so I can put m back to the derivative. So I have the derivative of like this. So this is m r is zero, right? Now the derivative of something is zero. What does that tell us? If the derivative of something is zero, then something itself is
constant.
It's constant, right? With respect to what we are being derived. So if the derivative with respect to time of something is zero, then something itself is constant of time, right? So basically from this expression, we can write down that the dt of mr is constant. So it's a constant. And since mass is constant, I can pull it back outside. So I have m times dr dt, right? Which gives us p, right? So here we have m times v.
MV
and m times v is nothing but
P.
the linear momentum. So basically, the linear momentum is constant in any system or in any particle where there is no forces. Okay. So this is just a consequence of Newton's second law. I'm going to state the law this conservation law formally. If the total force, maybe I'm going to use red. if the total force is zero, and by total force I mean this includes the possibility that they are forces but they cancel each other. Yeah, so at the end the total force is still zero. If the total force is zero, the momentum is conserved. As simple as that. The linear momentum, I should say. The linear momentum is conserved. Okay. Is conserved. Okay. All right. So this is quite evident, yeah. I can just move to the next thing. Now,
Sir,
yeah.
sir, in the parenthesis, MV is equal to constant, not MR is equal to constant. In 7 line. Conservation of below the line of where we write conservation of linear momentum. Yeah, yeah. There is MV, not MR.
This one?
Yes, sir.
No, this is the derivative with respect to time of m times r is constant. Right? Because here, from here, this is just d dt of d dt of m times r, right?
Yes, sir.
And now, if I integrate this one time, I got d dt of m times r is constant. Now, I can put this d dt inside. I can put m outside since m is constant. So I have m times d dt of r. Now, dr dt is just v. So
Okay,
this
sir. I
is
got it. Yes, sir.
okay. Is it clear? Yeah.
Yes, sir.
All right. So next, I'm going to talk about the, well, we have defined the linear momentum. I should define an angular momentum. Okay. If I take a look at this system once again, let me just draw it again. Um, with X, Y, and Z. I have a particle here. Let's say that this is particle is denoted by this particle with mass m. Okay, so now suppose that the particle is subject to an external momentum. So we pump momentum from outside, yeah, or maybe the particle itself gains momentum somehow, yeah, and the momentum goes let's say here, example, yeah. So this has momentum. By momentum, I mean that it has, but it moves with some velocity. So we have momentum along this direction, yeah. So now we call that the system has what we call the angular momentum. In other words, I can define the angular momentum and all right, so the angular momentum around with respect to what, yeah, angular momentum with respect to what. So I'm going to define it with respect to the origin. So this is the origin. Let's call the origin point O. Okay, the origin is point O. Sorry. Sorry, I'm answering my WhatsApp. Okay. So yeah, the angular momentum with respect to this point O is defined as the notation is L, and this is a vector. Yeah. Why is it vector? Because it is defined as the cross product between the arm of the moment, yeah, or in other words, this is just the position vector and
Linear momentum.
the momentum. Sorry?
I said linear momentum, cross product of
Yeah.
position and linear momentum.
Yes, linear momentum. Okay, so this is the definition of angular momentum. From this, we can directly derive or define what we call torque. Yeah, torque or moment of force. Yeah, torque or torsion. Well, maybe I'm going to call it torque. Torsion has slightly different meaning in mechanics. Yeah. So in order to avoid confusion, I'm calling it torque. Now I define torque with the symbol n, and this is also a vector. N is given by cross product of r and not p but f. So f is the force. So for example, if this object is subject to a force along this direction, for example, then there exists torque that works on this object here. But now, from the definition of torque, I can elaborate further, yeah, since we know that force is just from the Newton's second law, yeah, force is just the first derivative of momentum with respect to time, right? From the Newton's second law. Sorry, yeah, from Newton's second law above, yeah. Now we can write down. So this is something cross product with something else. Okay. And now from your mathematical methods in physics course, we know that this is something times the derivative of something else. So using the Leibniz rule, right? If you have, for example, A cross dB dt, right? This is the same, or maybe I'm going to put it another way. I'm going to, if I have A cross B, and I'm taking the derivative of both with respect to time, so this is just the same as dA dt cross B, right? Plus
Yes.
A cross dB dt, right? So applying it here, this can be seen as A cross dB dt. So this is the same as writing down d dt of r cross p, right? Minus dr dt cross p, right? Okay. But what is r cross p here? What is it?
Angular momentum.
This is just angular momentum, L. And what is this? Anyone knows what is this?
This
This is equal to 0, I think so.
0. And why? This is correct, but why?
Same cross product, V cross V.
Since this is just V, right? And we know that P contains V as well, right? M times V. So basically, this is V cross itself, V cross V. And we know that V cross V is 0. Or any vector cross product with itself is always 0. Okay, so this term is always 0. So basically, the torque is just the rate change of angular momentum per unit time. All right. So we have the result, the relation that this is just dl dt, right? And this is basically the same, or not the same, but equivalent or analogous to the case of linear force, right? We have force is just the rate change of linear momentum per unit time. So now we have torque is equal to the rate change of angular momentum per unit time. Okay. From this relation, we can directly derive the conservation of angular momentum, right? If so we can say that if the left-hand side is 0, yeah, if the total torque is 0, in other words, there is no, or there are torques, but they cancel each other, yeah, is 0, then the angular momentum is conserved, yeah. The angular momentum is conserved. Right, as we can easily see from here, is that if this is 0, then this is just dl dt equals 0, which means that L is constant. And this is what we call the conservation law of angular momentum. Conservation of angular momentum. Angular momentum. Okay, question? This is pretty elementary, yeah?
Yes, sir.
Now, next, I'm going to define work, right? Work. What is work? In physics, obviously.
F dot D.
Sorry?
F dot D, the dot product of.
Okay,
force
but
and-
what does it mean physically? I have a mass here, and then suppose that the mass is subjected to a force. This is given a force here, such that the mass or the particle moves,
Yes.
yeah, from one point to another. Okay, let's say that this is point 1. Say that it moves to point 2, right, along some displacement. Yeah, this is the displacement. Yeah, the total length is the displacement. The displacement means just the scalar of position vector. But if we take the what do you call the infinitesimal displacement, then we can define the dr. Yeah. So now work can be defined, work between point 1 and 2, yeah, as the integral from 1 to 2 of f dot dr. In other words, work is the force that acts upon a system or a particle along some displacement, right? So the requirement for the existence of work is that first the force must exist, second the displacement must occur. Okay, if any of these two doesn't happen, then the work is zero. Okay, so these are how we define work.
Excuse me, sir.
Yeah.
Is it necessary that the force direction will be in, or the displacement direction and force direction, they will be in the same direction?
No, it's not necessary. That's why we have the dot product here. So the component of force that will contribute to the work is just the component of force that is along the displacement. Like for example, here they make an angle. Sorry, they make an angle right here. They make an angle here, theta. So the dot product here means that I have to consider the component of F that is along the displacement. Okay. So now, yeah, question? Any question about this? So you can have the force and the displacement arbitrarily. Yeah, they don't have to be in the same direction. Then the component of force that is along the displacement, that will contribute to the work. The component of force that is perpendicular to the displacement does not contribute to work. Okay, it will contribute to the torque. Okay, not the work. Now we can elaborate this equation. If, as in the most cases, m is constant, then we can I can just write down the integral like this. Yeah, we know that I can open f is just the d dt of m times v, right, dot dr. So in most cases m is constant. I'm going to use this in order to not to be very strong. I can pull m out of, sorry, too many curly. I can pull m out of the integral. So this is just dv dt dot dr. Now obviously dv dt is the acceleration. Yeah. By the way, I didn't define acceleration above, but I'm sure you all know the acceleration is just the first derivative of position of velocity with respect to time. Yeah, or the second derivative of position with respect to time, the acceleration. So obviously dv dt is acceleration, but I'm not going to write it as an acceleration. Instead, I'm going to change this using the chain rule. Yeah, the chain rule in calculus. So this is dv dt dot, I can write down as dr dt times dt. Okay, so these are two. This is the first, this is the second. Okay, something like that. Now, what is dr dt? Dr dt is just v, right? So this is just v. So we have dv dt dot v, right? Inside the integral, we have dv dt dot v integrated with respect to time. Okay, what does this term inside the parenthesis mean? You see here that
Again, zero,
why?
because they are the same velocity, both are velocity.
Well, first of all, this is not the velocity and the velocity, but this is the derivative of velocity and the velocity. The second, and more importantly, this is dot product, not cross product.
Okay, yes. Yes,
So
sir.
it's not zero here. But you can see that, suppose that I have, let's say I have A squared. A squared is just A dot A. Yeah. So A squared is achieved by dot producting a vector A with itself. Okay. Now what would happen if I take the derivative of A squared? What would I have here? That is the same as taking the derivative of this one, right? You will get this is 2
And
times
a
A
power 1
dot dA
by
dt,
d2.
right? This is when you take the derivative of this with respect to t, you get this one. 2, well, because these are identical, so taking the derivative of here times this plus this times the derivative of that is simply 2 equal terms, so they're just twice the a dot dA dt, right? So if you see, this is something similar, but there is no 2 here. So I have to compensate for 2 by putting half. And here, I'm writing that this is just the dt of v squared, where v squared is just v dot v. Okay, v squared is just v dot v. So now I can write down like this: 1, 2. This is d dt of v squared dt. Now using the chain rule again, d dt of something times dt using the chain rule can be written as d of something itself, right? So what is the integral of d of something? If you have d of something, the total differential of something, right, so let me if you write down this one, so integral of this is just v, right? So this, when you open it, you have v squared. Evaluate it at position 1 and position 2. Sorry, I have half here, right? I pulled the half out. So this is just half times m v2 squared minus v1 squared. Now, defining, let us define T. T is what I call the kinetic energy, as half times m times v squared. So you can see that, you know that the left-hand side is W, the work. So the work can be written as T2 minus T1, right? Question? Or in other words, I can just write it down like this. This is just the delta T. The delta T means that T2 minus T1. On the other hand, this is the result if I use the force F, writing it like this, written like that. If on the other hand, I'm using the force coming from conservative, if the force is conservative, yeah, it can always be written like this, right? This is what I call the conservative force. Conservative force, right? So this is the minus gradient of the potential, right? Anyone not familiar with this symbol? This is the gradient, okay? So any conservative vector can always be written as the gradient of scalar. So the v here is a scalar, and the v here is what I defined as what we call the potential energy. The potential energy. Now, what happens if I'm putting F like this? So the force, the work is just minus integral of dot dr, right? And from mathematical methods in physics, you know that this is just minus integral of v. So this is capital V, to avoid confusion with small v. Small v is the velocity, capital V is potential energy. All right. Sorry, this is dv, right? This is just, so grad v dot dr is just dv. You can find it in your mathematical method in physics course. So what does that mean? This simply says that the work done is the difference between the potential energy at point 1 minus the potential energy at point 2. This is just minus delta V, right? Minus because now 1 is in the front, 2 is in the back. So if I join them together, I have T2 minus T1 is equal to V1 minus V2. And that means T1 plus V1 is equal to T2 plus V2. So what does that imply? So if I'm defining the sum of kinetic and potential energy as the total energy, yeah, the total energy. So this means that the total energy is constant. So this leads us to what we call the conservation of energy, right? The conservation of energy is stated as this one. If the forces are conservative, yeah, and no, just this requirement, yeah, then the total energy, and as you see, this is the same, it doesn't change, yeah, the sum. So the kinetic energy may change over time, right? But the change in kinetic energy is compensated by the change in potential energy as well. So the total sum of the kinetic and potential energy is always the same. So even though the kinetic energy or the potential energy individually are different from time to time, the sum of the kinetic plus plus potential is the same all the time. So this is constant, right? So now the total energy is conserved, and this is what we call the conservation of energy. All right, I think I have my colleague is calling me to talk about something. Yeah, so I think I'm going to stop here. We are going to continue on Wednesday. Any question so far?
No, sir.
Okay. If there is no question, I'm going to stop sharing, and maybe I'm going to stop